Greetings, everybody. This is the first video from Chapter 2 in the OpenStax text. Chapter 2 deals with one-dimensional motion with constant acceleration. Um, and so at this point, we're not going to really worry about vectors until we get to Chapter 3. And so right here, with one-dimensional motion, it's going to be um, motion in the x direction, or motion in the y direction, and we'll focus on a particular type of motion in the y direction called free fall, and then motion along an incline as indicated by this this arrow here. And one-dimensional motion, simply put, it's motion in a straight line. Well, let's deal with motion in the x direction first. Well, we know velocity is simply change in distance over change in time, delta x over delta t. Well, the change in any quantity is always the final minus the initial. So what we have is v is equal to delta x over delta t. Well, what is delta x? Xf minus xi, meaning x final minus x initial, the final position minus the initial. Well, what is delta t? Well, t final minus t initial. Well, typically in all the problems that we'll ever solve, t initial is 0. And so we're not going to worry about a TF and a TI. We just have T. So V is XF minus XI over T. In other words, change in distance over time. Well, what is acceleration? Well, we know acceleration is change in speed over change in time. Delta V over delta T. Well, what is change? What is delta V? VF minus VI. And delta T, we know, is simply just T. Well, the MKS units of speed, MKS meaning meters, kilograms, seconds, in i.e. the metric system. The MKS units of speed, i.e. v, is meters per second. The MKS unit of acceleration, i.e. change in speed over time, is meter per second squared. So you have a meter per second, meter per second squared. Now we're going to deal with one-dimensional motion problems where the acceleration a is constant. Well, that means you can have two cases. Um, you could have an acceleration of 0, meaning 0 is a constant number, meaning constant, meaning it does not change. Well, if a is 0, that just means that the speed is constant. Remember, what is acceleration? Delta v over t. Well, if the acceleration is 0, it means that delta v is 0, meaning v is not changing. So, and that's a very trivial case. If a is equal to 0, then v is constant. Now, a could be a constant, but either a positive or negative value, but not 0. And in that case, the velocity versus time graph will be linear, and the slope will either be positive or negative. But that's, in other words, the acceleration is constant, but not 0. So it could either be a constant positive value or a constant negative value. But in either case, the v versus t graph will be linear, and the x versus t graph will always be a parabola. That's the question to the math, the MAQ. One-dimensional motion with constant non-zero acceleration. The position versus time graph will always be a parabola. Well, here's a little sketch just in panel A. Notice here the speed is constant, meaning A is 0. In panel B, and what we're doing is we're assuming that between each of the arrows, the time interval is the same. Whether it's panel A, B, or C, the time interval between each frame is the same. So in panel A, notice the arrow representing the speed. Notice that arrow, the magnitude of that arrow is not changing. And notice that at each time interval, remember, the time interval between each frame is the same. And notice in each frame, the car is the same distance, travels the same distance. So in panel A, V is constant. Now in panel B, you can see that the acceleration is positive. See the speed is increasing. And notice the arrows representing the acceleration are the same length. See, the purple arrows are all the same magnitude, meaning here a is constant but not zero. And note it means so that's a positive acceleration. Notice the car and remember the time interval between each frame is the same. And now in panel C, the acceleration is constant, but it's negative, meaning the car is slowing down. Notice, see the speed here, the arrow representing the speed. Notice its magnitude is getting smaller, i.e. the car is slowing down. That's a negative acceleration, also sometimes called deceleration. So we have, just going back, we have V is x final minus x initial over t. A is equal to V final minus V initial over t. Again, obviously the units on distance, whether it's x or y, or distance d along an incline. The MKS unit of distance is a meter. The MKS unit of speed is a meter per second. The MKS unit of acceleration is a meter per second squared. Well, with these equations, with you have x, then you have v is xf minus xi over t. A is equal to vf minus vi over t. Well, we can derive. Oh, before I get to that, I got ahead of myself. I apologize. Well, let's look at the graphs. Let's look at the graphs of x versus t, v versus t, and ax, just meaning right now we're dealing with 1D motion in the x direction. Well, let's look at the graphs if ax is constant, but it's positive. Well, again, here the first graph is the distance, x versus t. Notice it's a parabola. The maroon curve, it's a parabola. Let's go back to the... now let's look at the second graph, the v versus t graph. Remember, in this case, the acceleration is positive, but it's constant. I mean, it's constant, but it's positive. So here, the v versus t graph is going to be linear with a positive slope. And the a versus t graph is going to be a slope of 0 because a is constant. It's not changing with time. It's remaining at the same positive value no matter what. So it's linear with a slope of 0. Okay, so that's so again the 1D motion, constant acceleration. Again, not zero. A is not 0. The a equal to 0 case is trivial. That means v is constant. So the distance versus time graph will always be a parabola. The v versus t will always be linear with a positive or negative slope. The acceleration versus time graph will always be linear with a slope of 0. Well, we can derive what are called the one-dimensional kinematic equations. And the key is they're only good if the acceleration is constant, which is the only cases we're going to consider. Well, I just call them equations 1 through 4. I number them in the order that I write them. So equation 1, x final equals x initial plus v initial t plus 1/2 a t squared. Equation 2, vf, and again, f is final, I is initial, vf equals vi plus at. Equation 3, vf squared equals vi squared plus 2a parentheses xf minus xi. Fourth equation, xf equals xi plus 1/2 parentheses vi plus vf close parentheses times t. Now we can derive them. The derivation is not terribly difficult, but it's important that we have them. You know, the derivation is secondary. And again, I just call them, when I refer to equation 1, it's the order in which I write them. I always write them in this order. That's 1D kinematic equation 1. xf equals xi plus vit plus 1/2 at squared. 1D kinematic equation 2, you get the idea. 1D kinematic equation 3, and 1D kinematic equation 4. Now, in most of the problems, not always, but in the majority of the problems, the object will start from a position of 0. In other words, xi will equal 0. And so so that means the xi term is just gone, and you can just drop the xf, you can just call it x. But notice that equations 1, 2, and 4 have t. Equation 3 does not. And the idea is you only have 4 equations, and we'll look at this example, you look at what you're given, what the problem asks you to solve for, and you have a 1 in 4 chance of starting with the correct equation. I mean, the odds are essentially in your favor. Well, let's look at an example. So here are 4 kinematic equations, 1 through 4. Again, I numbered them in the order in which I write them. So just starting 1, 2, 3, and 4. Okay. Example 1. So we have a jet. It's landing on an aircraft carrier, and it's landing at a speed of 140 miles an hour, which is in MKS units is 63 meters per second. I want to know what is the acceleration, and again, in all these 1D problems, the acceleration is going to be constant. If it's not, that's essentially a graduate level problem. So you don't ever worry if A is not constant. So we want to know what is, in part A, we want to know what is the acceleration if it comes to a stop in 2 seconds due to this arresting cable. Well, remember, if it stops, what does that tell you about V final? That tells you that V final is 0. Well, it lands on the aircraft carrier at 63 meters per second. That's your V initial. So you know you're given VI, VF, and we know that it stops in 2 seconds. So that's your time. And again, in this case, at the instant it lands on the aircraft carrier, we set that initial position equal to 0. You know, because essentially, think of a football field. It doesn't matter whether a player runs from the 25-yard line to the 50-yard line. They've gone 25 yards. Or if they go from the goal line, if they go from 0 to the 25-yard line, they still traveled 25 yards. So again, most cases we can just set xi equal to 0. All right, so we know vi, we know vf, and we know t. Well, look at equation 2. We know vf, we know vi, and we know t. And notice part A is asking for a. So clearly equation 2 is the starting point. So for part A, in other words, I want a. So first write the equation. This is the rubric. Vf equals vi plus at. Notice I've drawn this arrow through Vf saying, hey, Vf is 0. Why? Well, that's given in the problem because it stops. So step 1, Vf equals vi plus at. Next line, what is Vf? Vf is 0. So 0 equals vi plus at. We want to solve for a. Well, basic algebra, a is simply equal to minus vi over t. So you have your minus sign. That's due to the algebra. Actually, this. Let me pause this video for a second. Okay, so we need to solve. So again, Vf equals Vi plus At. Well, what is Vf? Vf is 0. So we have 0 equals, I don't know why that's there. 0 equals Vi plus At. Solve for A. Basic algebra. A is minus Vi over T. Plug in the values, MKS only. We know Vi was given as 63 meters per second. The time was 2 seconds. You get negative 31.5 meters per second squared. Why is A negative? Well, it's slowing down. It's stopping. It's sometimes called deceleration. Okay, now part B. Assuming again that when the jet touches on the plane, that's xi equals 0. What is the final position x? How far has it traveled along the aircraft carrier? So I want x. Well, I could actually use any of the other 3 equations. I used equation 2. So I'm done with that equation. Now, I could use equation 1, 3, or 4 to get x. Because I know the acceleration from part A, and I know VI and VF were given. So this is, I could use equations. So I could use 1, 3, or 4 to get x. I'm going to use 4. And remember, xi is 0. We know vf is 0. And we're just setting Just calling x final, just calling it x. Why use confusing subscripts if we don't need them? So let's look at equation 4. And that's the general equation. xf is equal to xi plus 1 half parentheses vi plus vf times t. But xi is 0, so that goes away. Vf is 0, so that goes away. And so x is just 1 half vi times t. And plug in the numbers. 1 half, vi was given, we know t. You get 63 meters. Well, let's check our answer. Let's go ahead and let's check it with equation 1. X, remember, again, xi is 0. So x is VIT plus 1 half AT squared. Let's go ahead and check it with that. VIT plus 1 half AT squared. Plug in the numbers. Remember, A was negative. You want to be a little bit careful. Remember, A was negative. So you get 63, so, I mean, you can crank the numbers. It's trivial, but you notice you get the same answer. Well, let's look at one more out of the OpenStax text. Here we have this is a standard example where we're going to apply kinematic equation 3. So you have a well-thrown ball is caught in a padded catcher's mitt. So the deceleration of the ball, in other words, the ball is accelerating, but then when it hits the catcher's mitt, the ball has an initial speed. When it hits the catcher's mitt, eventually the ball will stop. So the catcher's mitt causes the ball to slow down, i.e. to decelerate. So the deceleration is A is minus 2.1 times 10 to the 4th meters per second squared. And it takes 1.85 milliseconds, 10 to the minus 3rd seconds, from the time the ball first touches the mitt until it stops. Oh, it stops. Right away, what do we know about VF? It's 0. So part A, I want to know VI. What is the initial velocity of the ball? Well, again, let's look at what you're given. You know that the acceleration is minus 2.10 times 10 to the 4th meters per second squared. How do you know that? Well, it's given. Okay. Now, what is the time? Well, the time is 1.85 times 10 to the minus 3rd seconds. Remember, just be a little bit careful. The prefix milli is 10 to the minus 3rd. Now, VF is 0. Again, why? Well, nothing complicated. The ball stops. It first touches the mitt, and then obviously it comes to a stop. So I want VI. Well, again, probably the easiest one is equation 2. VF equals VI plus AT, because I know T, I know A, and I know VI. I know VF, I know A, and I know T. And I want VI. I misspoke a little bit. Remember, VF is 0 because the ball comes to a stop after it encounters the catcher's mitt. So equation 2, and so you end up with VI is equal to minus AT. It's very trivial to show that because, again, VF is 0. So you get 0 is equal to VI plus AT. You want VI, bring the AT term to the other side. It becomes negative. So VI is minus A times T, right? Now that minus sign, this minus sign is simply a result of the algebra. But A itself is negative. So you don't get confused over the minus signs. So VI is minus AT, so minus. A itself is negative, so you get a minus. You get the two minuses, become positive. Remember, the time is milliseconds, 10 to the minus 3rd. You get 38.9 meters per second. Now, what distance x does the mitt compress when the catcher catches the ball? Well, let's use equation 3. And remember, again, usually we can set xi equal to 0. We know VF is equal to 0, again, because when the ball hits the mitt causes the ball to decelerate. Eventually, the ball comes to a stop. So, again, xi 0, VF 0. So here's equation 3. This is the general equation. VF is 0. X initial is 0. So our distance is just x final, i.e. just x. So you get 0 is equal to vi squared plus 2ax. Algebraically, solve for x. Well, you want to bring the vi squared term to the other side. Just be careful, it now becomes negative. But it's negative, and then inside the parentheses you have vi squared. Then divided by 2a. So then plug in the numbers. So it's negative, but then inside the parentheses, it's 38.9 meters per second squared. So it's not negative vi squared. It's the negative of vi squared. So the minus sign is outside the parentheses. Then 2a, remember a is negative. So you get, if you plug in the numbers, you get 0.0360 meters, which is fine, and typically with these small distances, that's 3.60 centimeters. Now you can go ahead, something to try on your own, use equations 1 and 4 to get x, and see if you get the same value. Go back to kinematic equation, use equation 1, or use equation 4 to get x, and see if you get the same answer, and you will. So that's the 1D, again, they're known as the 1D kinematic equations. In this case, it's one-dimensional motion in the x direction. And they're only valid for when the acceleration is constant, which, again, that's all we deal with in Physics 1111. Alrighty, so let me go ahead and save this video, and I'll try to keep them around 15 minutes. 22 is a little bit longer, but that's okay. But let me go ahead and save this video and get it posted.